So regarding drift velocity, firstly I will discuss the concept. Suppose I say this is a conductor, any cylindrical conductor, and it is connected to supply. As we have discussed, when this key is open, then electrons are moving randomly in different direction, and we have discussed that speed is known as a thermal speed. Now I say this supply is of V volt, then definitely this end will be V potential or V volt higher compared to this end, and electric field is directed from high potential zone to low potential zone. If we observe any electron in the lattice, this electron will experience the force EE toward this side, because electron experience the force opposite to electric field, that we know very well. Now, as this electron try to move from right zone to left zone, they also collide with the ions of the lattice and they experience the opposing force F, and this opposing force depends on velocity. More the speed, more the opposing force, and you can say this F can be written as kV. K is the constant. Now what is the acceleration of the electron? You will say acceleration net is given by E minus opposing force kV upon m, that is the mass. Okay. Now due to acceleration, what will happen? You will say due to acceleration, electron speed will continuously increase. When electron speed will increase, opposite force F equal to kV, that will also increase. Then acceleration is decreasing. So you will say acceleration is decreasing, and at some particular speed, or you can say at some maximum speed, there may be possibility that acceleration is 0, and when acceleration is 0, you will say EE minus kV equal to 0. This V is written as EE upon K. Okay, and this is constant. E is constant, E is constant, K already we have taken constant. You will say this is constant. This constant speed is known as drift speed, and if drift speed is constant, we will say current is also constant. Okay. Now from this expression you can also say that V is proportional to E, and you can say this drift velocity is written as mu E. Here constant is mu. Mu is known as mobility of free electrons in the matter. Okay. So again I am repeating what we observe. Electron will not continuously accelerate. They will accelerate only for short time, and finally they will attain a drift speed. Okay, and when they will attain the drift speed? When electric force E and force due to collision, that I have written kV, is balanced. I hope it is clear to you. Okay, now we will further go. Now you read the definition. Drift velocity is defined as the velocity which is the free electron get drifted towards the positive terminal. Or you can say drift velocity is the average uniform velocity acquired by free electron inside the metal by the application of electric field. Like this. This is the cylindrical conductor of length L. There are two ends A and B. A is at high potential. Electric field always from the high potential zone to low potential zone. Then electron drift opposite to the direction of electric field. I hope it is visible to everybody. And opposite to the direction of flow of electron, we say conventional current or electric current. Now, drift velocity we have discussed is very small because they accelerate only for short interval of time. It is order of 10 to the power minus 4 meter per second. And thermal speed is very high, we have discussed in the last slide. It is given by this formula, and it is order of 10 to the power 5 meter per second. But for individual electron, thermal speed is there. For average electron, average thermal speed is 0. In absence of electric field, I discussed you when we touch, there is no current because average thermal speed is 0, or you can say this answer. Now we will derive the expression for drift velocity. Here we say there is a conductor, like same cylindrical conductor, and there are number of free electrons. They are moving with thermal speed U1, U2, U3, U4 and so on. As we have discussed, individual electron have high amount of thermal speed, but if we say average thermal speed, it is 0 due to random orientation. It means if I say I calculate the average thermal speed, it should be 0. Okay. Now you give the supply an electron accelerate, and we have discussed that speed is drift speed. Suppose I say first electron speed for a time τ1, then velocity of the first electron can be written as u1 plus a τ1. For second electron, initial speed is u2, acceleration is same, relaxation time is τ2. Similarly for the third electron, u3 plus a τ3 and so on. Firstly, I will discuss you what is relaxation time. Of course, we have discussed in class 11th also, but here I will discuss in brief what is relaxation time. What you will say? You say this is your cylinder, and suppose electron travel from this point to this point, straight path, no collision from point A to point B. So when electron travel from point A to point B, no collision is there. This path is known as free path. Electron is free, and time taken to travel this path is known as free time or relaxation time, because electron is relaxed during this time. Okay, but you say collision is random, like I say like this. It means what we are observing, relaxation time is not constant. Somewhere it is short, somewhere it is long. So what we do, we take average relaxation time for all calculation. That is known as the mean relaxation time. So if I write mean relaxation time, you will say for mean relaxation time, you will say average of this individual relaxation time like this. What is n? N is the number of collision or number of electron, you can say. Now one more thing I want to tell you, this relaxation time depends on temperature. If we increase the temperature, then speed will increase, all of you know, and relaxation time will decrease. I hope it is visible to all of you. Now again I am going to the drift velocity expression. If I say I have calculated V1, I have calculated V2, V3 and so on. What is average drift speed? V average can be written as V1 plus V2 plus V3 divided by n. What we calculate? U1 plus U2 plus U3 upon n plus A τ1, τ2, τ3 divided by n, and we have discussed this is 0, so I will say Vd equal to A. This is mean relaxation time I have discussed earlier. Now we all know force is known as for the electron E. I am talking only magnitude. This should be equal to ma, so I put the value of the A. We get the final result E τ upon m. This is expression for drift velocity. So all of you just check it. This is the expression for drift velocity. Okay. The relation between current and drift velocity. Suppose I again assume the same situation. This is a cylindrical conductor and it is connected to any supply, because when supply is there, definitely drift velocity will be there. So directly we connect it without help any key. Okay, and I say A is the area of cross section. Area of cross section. Suppose I assume this. Now I assume two cross section. I name it P and Q, and distance between them is drift Vd. Okay, what is Vd? Vd is the drift velocity, and I say I assume distance between two cross section is also Vd. I hope it is clear to all of you. No. If I say n is number of free electrons per unit volume, number of electrons per unit volume, then can you tell me in this cross section how many electrons are there? Okay, so I write here total number of electrons between cross section P and Q. You will say n is the number of electron per unit volume, and volume of this part is written as area into distance. We have second Vd is the distance. Okay, this is the total charge. This is the total charge. So sorry, this is total number of electron. Now charge on each electron is E. Then what is the total charge in this volume? These are the number of electron. Charge on the electron is E. Total charge is given by NeaVd. It is clear? Now listen. The electron which is at the cross section Q at present will reach the cross section P after 1 second. Why? Because we have selected P and Q such that the distance between them is Vd, that is the drift speed of the electron. Okay, so this total charge NeaVd is the charge which will pass through the cross section at P, where P can be any point on the conductor. Hence this is the electric current flowing through the conductor, and we say I equal to NeaVd, because this is the total charge which is traveling in 1 second, because Vd is the drift speed and I have taken Vd as the distance. Now if I ask you current density, you will say J equal to I upon A. What you will get? NeVd. It is clear? Let me show it on the next slide. So all of you just read it. Relaxation time I have discussed earlier. You have to just remember these formulas for your numerical purpose. Free electron density, how will you calculate? Now, what is the question? The electron drift arises due to the force experienced by electron in the electric field inside the conductor. But force should cause acceleration. Why then do the electrons acquire a steady average drift speed? I think I have discussed you a lot. One force will support the motion, that is E. Another force which I have discussed, that is kV, that will oppose the motion. So they acquire a steady average drift speed. All of you can read it. If the electron drift speed is so small and the electron charge is small, how can we still obtain large amount of current? I think all of you know the formula. I equal to NeVd. If electron drift speed is small, Vd is small, charge of the electron is also small. Then how can we obtain large amount of current in the conductor? You will say it depends on N. Electron density in the conductor is very high, approximately 10⁻29 per cubic meter. Now I am discussing you with one animation. How fast is an electron in electricity? We go through the animation.
How fast does an electron move down a wire? Which would win in a race, an electron or a snail? Let's answer the second question first. You may be surprised to learn that the snail would win, easily. Let's use this electrical circuit as our racetrack. It has an on-off switch, a battery, and a light. The distance around our racetrack is 22 inches. According to the 1999 World Almanac and Book of Facts, a garden snail can move at a whopping 0.03 miles per hour. That's 0.528 inches per second. We'll call her Joan. The 1998 Guinness Book of World Records says that a garden snail named Archie went a whopping 13 inches in 2 minutes. That's 0.108 inches per second. This is Archie. And here's our electron. We'll talk about how fast it moves later. And they're off. Archie and Joan roar ahead with the electron. Well, it's moving, but doesn't look like it yet. Joan's in the lead, and Joan zooms ahead with Archie behind, and then the electron... Well, this will take all day, so let's fast forward it. And the winner is Joan, with Archie well behind, but our electron has moved a mere 1/10 of an inch. But doesn't electricity move at the speed of light? The speed of light is around 300,000 kilometers per second, or 186,000 miles per second. Actually, in an unshielded copper wire like this one, electricity moves at around 96% the speed of light, so 178,560 miles per second. At that speed, ignoring other losses, electricity could circle the globe over 7 times in just 1 second. So electricity moves at close to the speed of light, but the electrons don't, as we saw with our little racetrack. One way to visualize what's going on is to use this row of marbles. When we push on one marble, the effect of that push is passed on from marble to marble, and the result is felt by the wooden tile almost immediately. The individual marbles represent individual electrons. They don't move very far along the way. Electricity is represented by the effect on the wooden tile. That effect is passed on almost immediately. And to answer our other question, how fast are the electrons moving? The electrons move at a velocity called the drift velocity. Here's one easy formula we can use to find out. Calculating it out, we get 0.0007 meters per second, or 0.0028 inches per second. Remember, our slowest snail, Archie, goes 0.108 inches per second, 38 times as fast as the electron. For the electron to go around our 22-inch long track, it would take 7,857 seconds, or around 131 minutes, ignoring the time spent in the battery, switch, and light. Electricity from a battery is direct current electricity. The electrons go around in one direction. Electricity you get from your wall socket is alternating current electricity. The electrons go one way, stop, go back the other way, stop, and go the other way again. Even here, though, the electrons are moving slow, like we've been talking about, even though the effect, the electricity, moves very fast.
So I think in a nutshell, we can say when you switch on the plug and light starts in the room, you can say this wire is just like the pipe which is full of water. As you open the tap from one side, water starts to fall down from the other side. So this wire is full of electrons. Now one more question. When electron drift in metal from low to high potential zone, does it mean that all the free electrons of the metal are moving in the same direction? You have to say no. Not all the electrons move in the same direction. Basically, drift velocity is a superposition over thermal speed. So just read it. How do metal conduct electricity? It is the delocalized electron involved in metallic bonding that allow metal to conduct electricity. The delocalized electrons are free to flow through the metal and they carry current. Insulating material do not contain free electrons and so current is unable to flow. I can say these are known as localized. Let me change my cursor, please. This is localized. Okay. Mobility. Now we will discuss something about mobility. Mobility, I think we will discuss the formula in the last slide. Mobility, let me write correctly, mu equal to drift velocity per unit electric field. That is the mobility. And what is drift velocity? E tau upon m, and this is E. You can cancellizing E. Finally, this is a relation for mobility. So, mobility depends on first point. You can say it depends first point E by m. What is E by m? Specific charge. Okay. Second thing, it depends on tau. What is this? Relaxation time. And relaxation time depends on temperature. In bracket you can say it depends on temperature. Clear? Like this. Okay. Now I am asking one more thing. Are the path of electron a straight line between successive collision in the absence of electric field and presence of electric field? All of you just recall the first chapter, electrostatics. Motion of a charged particle in electric field. Yes. Path will be straight line when theta is 0 or 180 degree. I think all of you are recalling that situation. If electric field is uniform and this is the electron always experiences the force opposite to the electric field, then it may be straight line. And if this is the electric field, we have discussed there, and electron enter perpendicular or at any angle, the path will be parabolic or curved. But here you are supposed to say, in the absence of electric field, we will assume path is straight line, but in the presence of electric field, we will assume path is curved. Like I have shown here, in the left topmost diagram, this is the collision when there is no supply, straight line path. Right side we have drawn a starting point with one black dot and a point with another black dot. But again, we apply the electric field. When the electric field is applied from right to left, electron will experience the force toward the right hand side direction, path will be curved. Now you can see earlier start and end point and now start and end point. You can see this is displacement. This is known as drift. You just read the misconcept. I have told you. Again, we have discussed it. You pause the video and read it. Now, a steady current passes through a cylindrical conductor. Is there an electric field inside the conductor? I think electrostatics chapter we have discussed if this is a conductor. In the electrostatics chapter we have discussed if any charge is given, it will reside on the outer surface. And we have discussed net electric field inside is 0. Is same thing is here in a current carrying conductor? No. Here electron get the drift speed, and they get the drift speed due to the acceleration, and you say in this situation we will use the formula E equal to V by L. V is the potential difference, L is the length of the conductor. In this situation, outside the conductor, electric field is taken 0. Like this. Okay. Now I am asking one more question. You have to tell me true or false. First question. In an electrolytic solution, the electric current is mainly due to the movement of free electrons. You will say it is false. Why false? Because in electrolyte, current is due to the movement of both positive and negative ions. Next, electron in a conductor have no motion in the absence of potential difference across it. I hope all of you getting this statement is false, because we know in metal electron always have random motion due to thermal energy. Now I will discuss Ohm's law.